only for the sake of posterity, so that when people listen to this tape later on, they have a little bit of an introduction. Are you ready? Mm-hmm. Okay, so I'm happy to present our first speaker for the semester, David Blei from Princeton. David's a Brown undergrad, did his PhD with Mike Jordan at Berkeley, had a couple year stint at CMU where he worked with John Lafferty. Then he went to the faculty of Princeton, where he's now an associate professor of computer science. He came to my attention personally when he did some work on latent Dirichlet allocation. I was sort of late on picking up the work because I really noticed it only after he went to CMU to work as a postdoc with Lafferty. And then Lafferty came bragging about all this work, and then I said, who is the guy who's really doing it? And it was David. And so after doing the hierarchical Dirichlet allocation and some other topic models work at Berkeley, with Blei he did a lot of nice work on dynamical topic models. And then he went on more generally to work on non-parametric modeling. And he's done a lot of work since then. So typically people enumerate various accomplishments and awards. So for David, I won't do that. I'll simply say, as a student, he got Best Paper awards. And then he's continuing the tradition because now his students keep getting Best Paper awards. So without further ado, David Blei.
Thanks. Thanks for the nice introduction. Thanks for inviting me. Can you hear me? Great. So, someone say no. Speak up. Okay. I'm Dave Blei. I'm going to talk about scalable topic models. So, the idea behind topic modeling is that as more information becomes available to us, it becomes more difficult for us to quickly search and discover and find what we need. And so we need new tools, new statistical tools, new machine learning tools to help us organize, search, and understand these vast amounts of information. What topic modeling provides for us are methods of automatically organizing, understanding, searching, and summarizing large electronic archives of text, where they're applicable in other kinds of data sets too. The basic idea behind a topic modeling algorithm, it's sort of vanilla exploratory data analysis, is to first use a model to discover the hidden themes that pervade a collection, then to annotate the documents according to those themes, and finally to use those annotations to organize, summarize, search, do whatever it is that is one of the data set. So for example, with a topic model, we can discover topics from a collection of documents. Here, each column is a topic. I'll define what a topic is in a little bit. And these were uncovered by analyzing documents from Science magazine. Here's one topic about computer modeling. Here's a topic about diseases. Here's a topic about evolutionary biology. We can look at how topics change over time. So here is a different topic model. This is one I'll talk about a little bit later, where these patterns of word use change as the years progress of a set of publications. So here we have a topic about what I call theoretical physics, where you see the word laser increasing, the word force decreasing, the word relativity peaking at some point in the 50s. Here's a topic about neuroscience, where you can see the word nerve decreases in steam over time, the word neuron increases, and the word oxygen spikes here in 1950 or so. This is because they were doing experiments on people, depriving them of oxygen and asking them to solve math problems. And then, that fell out of favor quickly. Somebody caught wind, and then this is what happened. We can look at how topics are connected to each other. So here we have a graph of topics. Each of these is a little pattern of word co-occurrences. And a connection in this graph means that a document about this topic is also to likely be about this topic, at least more so than about something like this. So why do we do all this? Well, it's to help us organize and browse large archives of text. Again, remember the idea is to help us manage this massive amount of information that we're bombarded with. So here's an example of a browser built for the topic. Okay, so in case I don't get to the end of the talk, I want to tell you what I'm going to talk about. Existing algorithms for doing topic modeling work in what is called batch mode. They iteratively examine each document of the collection, update the idea of the model, and repeat that process. This is inefficient in an obvious way. Before getting your first iteration of a topic model, you have to look at every document in your collection. And our goal is to use these kinds of techniques to model massive collections of millions of documents, or even documents coming in stream. So what scalable topic modeling does is work by sampling one document, analyzing it, updating the model, and repeating. And how that's justified is the subject of this talk. This algorithm lets us link topic models to things like web APIs and databases with massive collections that don't fit in memory, for instance. It lets us handle millions of documents. And it lets us refine topic models on the fly, for example, in user interfaces. Okay, so in this talk, I'll start by giving you an introduction to topic modeling. Then I'm going to talk about some of our recent research in topic modeling, some extensions to the simplest model that we've been working on lately, and finally I'll talk about scalable models. Okay, so 2 screens is confusing for me, but let's go to this one now. Topic modeling is really just a case study in probabilistic modeling with big collections of discrete data that's the language. All right, and the idea, as in all statistical modeling, is to, as in a lot of statistical modeling, is to treat data as observations that arise from some generative probabilistic process that includes hidden variables. So in topic modeling, we're modeling documents, and the hidden variables is this latent thematic structure that we're trying to uncover. Then infer the hidden structure using posterior inference. So again, in topic modeling, that's asking what are the topics that best describe this collection, given the observed words of the documents. And then finally, to situate new data into the estimated model. So if I create a new document now, or a query, or something like that, how do I fit it in to the latent structure that I fit with posterior inference? Okay, and the simplest topic model is called latent Dirichlet allocation. And it works by a simple intuition that documents exhibit multiple topics. Okay, so here's an article. This is from Science Magazine called Seeking Life's Bare Genetic Necessities. I think I showed this slide last time I was here. And this is an article about determining the number of genes that an organism needs to survive in an evolutionary sense over tens of thousands of years. What I've done by hand here to show you this intuition is highlighted different words with different colors. So you can see I highlighted the word prediction in blue, and the word computer and analysis in blue, and computational words about data analysis I highlighted in blue. Words like organism, life, survive, words about evolutionary biology I highlighted in pink, and words about genes and genome, sequence, genetic I highlighted in yellow. These are words about genomics. So if I took the time to highlight every word in the article, except for function words, and you squinted, you would see that this article mixes blue, yellow, and pink. It combines these topics of evolutionary biology, data analysis, and genetics. So the idea with LDA is to take that intuition and translate it into a generative probabilistic model. Each topic will now define a topic to be a distribution over a vocabulary. So here are the topics that live outside of the collection of documents, each of which places different probabilities in all the words in the vocabulary. So the blue topic has words like data, number, computer with high probability. The green topic has words like brain, neuron, nerve with high probability. The pink topic has words about evolutionary biology with high probability, and so on. And these topics, each of which is a distribution over all the words, live outside the collection, as I mentioned. Now, for each document, what we do is, in this imaginary generative process, we first choose a distribution over topics. Okay, so here I chose the pink topic, the yellow topic, and the blue topic with different probabilities. And then, for each word, we choose a topic from this distribution. Here I chose a blue coin. We look up the distribution over words that corresponds to that topic, and then choose a word at random from that distribution. Here I chose the word analysis. Okay, and you repeat this process for every word in the document. Excuse me. Again, I emphasize this is an imaginary process. We repeat this imaginary process for every word in the document. Here I chose the yellow coin and the word genetic. Here I chose the pink coin and the word life. And you can see that with these assumptions, the documents reflect these topics with different proportions. Now we turn the page in science, and we repeat the process. We choose a new distribution over topics. This one might contain evolutionary biology and neuroscience, and repeatedly draw each word from the corresponding topics drawn from this distribution. Okay, notice also that the topics are shared across the whole collection, but each document exhibits those topics with different proportions. Okay, feel free to interrupt me with questions about this. rub is that we don't get to observe all this nice thematic structure. Remember, it's hidden structure. Our goal is to figure it out. And so all we observe are the words of the documents, and all of this other structure are hidden variables in the model I just described. What are the topics assigned to each word in each document? What are the topic proportions assigned to each document in the collection? And, perhaps most interesting, what are the distributions of words that best describe the collection under the assumptions that I just explained?
So do you assign to every word so you have a non-topic oriented distribution that has the and? Or
Well, so we just remove those from the data in advance. Yeah, so we're really modeling just the non-function words here. Okay, so that's the computational problem in this model, is to infer these hidden variables from the observed collection. Okay, in other words, compute the distribution of the topics, the topic proportions for each document, and the topic assignments for each word given the documents. Okay. So now, as a graphical model, LDA looks like this. Just to remind you, in a graphical model, vertices are random variables, edges denote possible dependence between random variables, shading indicates what's observed, unshaded variables are hidden, and plates denote replication of variables. So that story I just told you, I can tell you that story again with this picture. First, we have K topics that live outside of the collection. So each topic is called theta. Then for each document, we choose a distribution over topics, that's theta, those are the topic proportions. And for each word in each document, we choose a word from the corresponding distribution. Sorry, we choose a topic from the corresponding distribution over topics, and then choose a word from the corresponding topic distribution over terms. Okay, so C is like the colored coin that you saw in that previous picture. Beta are the distributions over words, and theta is the cartoon histogram of which topics the document's about and with which proportions. Okay? Graphical model really just encodes a factorized distribution over the ensemble of random variables in here. This is the factorized distribution of the hidden and observed variables in LDA. And again, this also induces a posterior. Our goal is to compute the conditional distribution of all of these unshaded things given the shaded things. Notice that the only observation we have is the nth word in the deep document. So that's our data. It's a bunch of documents, each of which is a collection of words. Also notice that we're not taking word order into account here. This is a bag of words model. All right, so let me just show you what these posteriors look like in practice. We took the OCR collection of science from 1990 to 2000, so that's 10 years of articles from Science magazine, 17,000 documents, 11 million observations, 20,000 unique terms, removing very rare words and stock words. And we estimated the posterior for a 100-topic LDA model using variational inference. That's an algorithm I'll talk about later in the talk. And so here's our original article that I already showed you. This is the posterior expectation of theta. This is the inferred topic proportions for this article. So just to be clear, I took 17,000 articles. We fit a big posterior. That includes a conditional distribution of theta given these words. And this is a picture of the expectation of that conditional distribution. Okay, so this is like the real histogram for this article. Notice that even though there are 100 topics that we could play with here, only a handful of them have been activated by the words in this article. And now we can take the topics associated with the topics that have high probability within this article and look at their most frequent words. And you can see that we have words about genetics, words about evolutionary biology, words about diseases and survival, and words about data analysis and computer modeling as being the most frequent words in the topics that are most frequently used in that document. Again, I emphasize that these patterns emerge by just analyzing the original documents. There's no prior information about what subjects might be in the collection, and so these models can be used to elucidate the subjects of any kind of collection that you might want to explore. Hey, here's another
just
example.
to be clear, those lists are the top few words in the data
That's right.
corresponding to the top few E theta in the document you showed us.
Yes, exactly. So this is expectation of theta given the words. Each of these is associated with a distribution over terms, and these are the most probable terms in those distributions. These words might not even appear in this document. Okay, here's another example of an article about mathematical models of insect movement, and here are the most likely terms and the most likely topics of this article. Okay, so that's a quick introduction to LDA. LDA can help us visualize the hidden thematic structure in large collections of documents and generalize new data to fit into that structure. LDA really builds on LSA, latent semantic analysis, and PLSA, probabilistic latent semantic analysis. It's like a Bayesian version of PLSA. And in statistics, this kind of model is called a mixed membership model. The idea being that each document is modeled as a mixture model, where the mixture proportions are document specific, that's data, and the mixture components, that's the topics in this case, are shared by the whole collection. And mixed membership models are used in a lot in things like survey analysis and social network analysis and many other settings. And I should mention that LDA was independently invented for doing population genetics. So where a very similar model was used to determine retrospectively how a population mixed among different regions of the world genetically. And Stevens and Pritchard have been working on that model for many years. It's a really interesting line of work. Okay, before going into the more technical stuff in the talk, I want to just show you some examples of open source implementations of LDA in case you want to play with this on your own. So one of my favorite ones is the LDA package in R that was written by Jonathan Chang. It's very fast, and basically you can take your documents one per line. Jonathan's code converts them, can convert it into a file like this, which is a sparse matrix representation of the word counts in each of your documents. And then with a few lines of R, you can get an LDA model that you can visualize the topics from. And it's very fast too. There's also an open source way of browsing documents from Alison Cheney, she's one of my students, where you can take the output of an LDA model and build a document browser of your whole collection from that output. Okay. That really concludes the introductory part of the topic model. So, why is LDA interesting? Why do we care about these kinds of models? Well, one reason is that organizing and finding patterns of data is becoming more and more important. We have lots of data. LDA, this kind of model can be easily embedded in more complicated models. For example, we can, rather than model words, we can model genetic data or images. Rather than use a bag of words model, we can model some kind of sequence information in the documents. Our topics don't have to be multinomial distributions. They can be Gaussian distributions, distributions of other things. There's a lot of places that we can change here. At some point, you cross the threshold. You're no longer doing topic modeling. You're just doing modeling. And that's a good thing to be doing. And so this is another reason why LDA is interesting. Another reason is that algorithmic improvements let us fit these models now to massive data. So now that we have massive data sets of all types, it's of interest to articulate assumptions via graphical models and then compute with those assumptions via posterior inference. So I'm going to tell you about an algorithm for doing that today. Okay, again, at some point you cross the threshold, you're just doing modeling. That's a good thing. And I just wanted to show you this picture because it's sort of how I think about the process of data modeling. Research in data modeling separates these basic activities. There's modeling assumptions, which is drawing circles and arrows in a way that makes sense to you. Collecting data, that just happens by itself. You don't have to even, sometimes I sign a form and then you collect data, but other times, probably everybody's collecting data about you right now. So the data and your modeling assumptions together give you, of course, a posterior distribution of the hidden variables that you assumed existed in your modeling assumptions. And a big problem is to infer the posterior. Once you have the posterior, you then use that to do a bunch of things. You can explore your data under the lens of the hidden variables that you inferred, which were inferred using your assumptions in mind. You can make predictions about future data. And you can and should check your assumptions based on the inference you make. So this is a gap we see in machine learning, that we often go right to prediction and exploration without checking our assumptions. And the reason is that it's really hard to check your assumptions. I took this picture. I love this picture. I've been really tempted to put it on a t-shirt, but then a little voice said, don't do that. And then I got worried about the little voice. But that picture is from a great paper by George Box. I think it's called Science and Statistics, and it's about predictive checking. So I'm not going to talk about it now, but I would love to. The idea is that you take your posterior that you inferred, generate data from a model that uses that posterior as its prior, and then see how close that data is to the actual data you saw. And if that data is far away in ways that are important to you from the data that you saw, that's a good clue that there might be something wrong with your modeling assumptions. So that's the idea of a predictive check. And prediction is well in line with predictive checking as well. So the papers to read about that are George Box has written a bunch of papers. Andrew Gelman, Don Rubin have papers about predictive checking that are worth reading. Okay, so though these pieces of probabilistic modeling are all linked, we can work on each one separately. So first I'm going to show you 3 ways that we've changed the assumptions based on different kinds of data and different models appropriate to those data. And then I'm going to show you a general way to improve inference, again in this picture where our inference algorithm can be used in a lot of different models. Okay, so first, the model I described for you assumes that there's one set of topics that describes the whole collection. But a lot of collections span many years, and it's unrealistic to think that the same set of topics would generate an article written in 1880 as would generate an article written in 1980. Dynamic topic models are a way to try to capture topics that change over time, and you can see in the graphical model that each vertical slice is the LBA model I just described for you, but now each topic is a slowly changing sequence of distributions over words. So here is 1880, and we have K topics in 1880. Then those K topics drift a little bit to 1881, and here we have the documents of 1881 generated by those topics. They go to 1882, and so on, all the way to the present day. Again, you can see our observations are the nth words in the D's document, but now the documents are time-stamped. And the posterior here gives us not just a collection of distributions over terms, but a sequence of distributions over terms, one for each topic. So for example, here's an article called Sequencing the Genome Fast. This is about the technology needed to sequence the genome, to sequence it quickly. And here again are the topics that were activated. This is the expectation of theta given the words in this document. I should say, so what I'm showing you is a fit to all of science from 1880 till 2001. It's something like 160,000 documents. And this is one document from 2001. Okay, we can play the same game. We can look at the topics from 2001 that were activated for this document, and you can see these are topics about gene sequencing and technology and devices, and again about computer stuff. Okay. Now, though, we go back to our model. Each of those topics lives in this sequence, and we can ask the question: what did that topic look like throughout the decades that was activated in this article? And so here's the devices, materials topic. And what you can see here, I'm plotting it for every decade, the top 10 words or so. So here it is in 2000, and you can see that this topic smoothly changed over time from things like electric machine, power, engine, steam, to things like device, materials, current, gate, silicon technology. And this is a more expressive model that can capture this type of changing patterns of word coordinates.
How did you correlate the topics, though?
Good question. So again, by fitting this model. So we didn't have to do anything special to connect the topics because our model already assumes that they're connected. So the way this model works is that, as I described, the topic begins somewhere, and then it's assumed that that topic just drifts a little bit to get to the next year, and a little bit to get to the next year. And so all I've done is said, okay, this was topic 52. Let me look at topic 52 throughout the years. And here is topic 52 throughout the years. This is the kind of thing that you can't really do by post hoc analysis of LDA models because there's no guarantee that you get the same kind of topic in two different fits of LDA. Okay, I bring it up, yeah.
So on your plate diagrams, is your capital N fixed? So every topic has the same number of words?
Yeah, I'm cheating a little bit. So every document does not have the same number of words. There's a little D here.
Or for that matter, each year doesn't have the same number of documents.
And each year doesn't have the same number of documents, yeah.
So what would happen if, in moving in time, you sort of windowed? So you took a 3-year span, but it had, but then you moved ahead a year
And refit the model.
and did another 3-year span.
You can do that. I think that's just as much work as fitting the model you want to fit anyway, because you still suffer from the problem of having to connect the topics in the second fit to the topics in the first fit. It's not clear how to do that. Certainly automatically, it's not clear how to do that. The methods for fitting these algorithms find the local optima of an objective function, and so you're not guaranteed that you're going to find a local optima that plays nicely with the local optima of the previous fit. Okay, so I bring up the dynamic topic model because I want to tell you about the model for measuring scholarly impact. This is joint work with Sean Garish. So the idea behind this model is that influential articles reflect future changes in how language is used. Okay, so here's the history of science in the x-axis, and here is impact in the y-axis. Okay, so Einstein develops the theory of relativity. We all know that that had a high impact. And here I developed a crackpot theory in physics at the same time as Einstein's theory of relativity. Well, as science moves forward, we should see a bunch of papers about relativity and very few papers that build off of my crackpot theory. Our idea here is that the influence of an article is a latent variable in this sequence of articles through time, and that influential articles should affect the drift of the topics they discuss. Okay, so both of these articles are about physics, but the drift of the topic about physics is more affected. I'm using the causal language loosely here. We don't really believe in any kind of, that we're capturing anything causal. But the drift of that topic is affected more by the words that Einstein used than the words that I used. Okay? Fitting a model that captures these intuitions, its posterior will give us a retrospective estimate of which articles were influential and which weren't. Okay, so now this illustrates both the blessing and the curse of graphical models. So taking these few statements, it was pretty easy to go to the whiteboard and draw this picture, but then it took like 2 years to figure out how to fit the model. But here's the idea. Again, we have topics drifting in time, just like in the dynamic topic model. We have documents each at different years, but now each document has this I variable. Okay, and that I variable is the latent influence of the documents. So Einstein's theory of relativity is back here somewhere and has a latent variable I, which connects to the topics in the next year. Okay, so the way this works is that a document with a high influence, its words, its observed words, which also connect to the topics, are going to play more of a role on how that topic drifts. I guess what I didn't mention is that in the first dynamic topic model I showed you, those topics are assumed to have zero mean drift in the modeling assumptions. And now we're basically nudging the drift through the words of the documents that have high impact. Of course, that impact is a latent variable, so what's happening is that when we're given observed data, we see how those topics tended to drift, and we assign high impact to the documents that seem to be predictive of that drift. That's the way it works. Okay?
Suppose the document is influential, but it's not influential in the next preceding year.
Good question. I didn't want to draw so many arrows, but really there's another parameter here, which is that we have a kind of an envelope of influence. It goes like 5 years into the future. But setting that and fitting that is something we don't quite know how to do well yet.
David?
Yeah.
Just really quickly, this is presumably very much the same TDT, the topic section and tracking sort of task, but maybe we'll identify sort of the first new scope of what's going to be a number of sequential news stories.
Well, that's another limitation. So there's no notion of a topic just appearing. It does happen that a topic gradually appears. It's gradually used more. But the idea of a topic appearing isn't built into this model. That would be an interesting innovation to pursue here.
In K, the number of topics is just a parameter you give it. You set 100 topics for all of time.
That's right. That's a parameter, right, and that's related to this issue. So there are these Bayesian non-parametric methods that we work on as well, where K is more influenced by another parameter, and you get kind of a windows of K that emerge out of the posterior. But again, here we're just fixing K.
Dave, do I remember wrong that you or maybe somebody else has married dynamic topic models with birth-death processes?
I think somebody else, I think EY Tay did that.
Okay.
Yeah, I'm not sure we know yet how to fit them at large scale like this, which is why we're still sort of setting K to be 100. But that's something we'll work on. We're working on that. The algorithm that I'm going to talk about at the end, we're hoping to move that into a dynamic topic model algorithm. Okay, so the results on this are interesting. So we took a bunch of corpora and did this model, and then we looked at this posterior value of the impact of each article in the collections. We looked at 3 collections. We looked at the proceedings of National Academy of Science over the course of some number of years. We looked at Nature magazine over the course of some number of years, and we looked at the corpus of computational linguistics papers. And what we found is that this measure of impact, it only uses the words of the documents, but it correlates with citation counts significantly. So we did all kinds of things, like we permuted the the number of citations and refit the model and got much lower values of correlation. We also, within a fit, permuted the citations and computed this correlation again. It passed all these tests. The test that it passed that was the most expensive test was to actually permute all the articles themselves and refit the whole model. And again, we found no correlation to citations. So there is real signal here, even though these numbers are like 0.15, 0.35 are the highest. And it's interesting to look at the results. So some papers had high impact value and high citations. So for example, the Mathematical Statistical Machine Translation, the Brown et al. 1993 paper, both was a highly cited paper, and we predicted it to be a high impact paper. Again, I don't know if I was clear. So there's no citations anywhere in this model. That's why this is a meaningful test of what the model's doing. But of course, 35% correlation is not 100% correlation. We miss a lot of articles that are highly cited. And one of the interesting ones was an article that introduced the Penn tree bank, Marcus et al., also from the same year, 1993. That's the most cited article in this computational linguistics corpus. And we don't detect it as having a high impact. even though many, many papers cite it as thousands of citations. And the reason is that this is a model of language impact. And this paper's impact is through introducing a data set to the community that then had a huge, was very important in developing statistical natural language processing. I mean, I can't be speaking to this audience about what happened in statistical natural language processing, so I'll stop soon. But it's not as though when you cite the Penn Treebank paper, you start using the words of the Penn Treebank. I mean, how many of you have read the Penn Treebank paper? How many of you have cited it? So, turn the camera around. Anyway, if you read this paper, it's all about the method of collecting the data. Okay,
So the kinds of impact you're measuring are repeating the words that appeared in that paper, or are you looking at several other probability distributions that seem to be affected by that?
Well, again, that's essentially what happens. If the way language is used if what you wrote in your paper is predictive of how the way language is used changed in the future, then we're calling your paper impactful. That's the way.
But I bet the high impact papers in the next few years were disproportionately likely to cite the Penn Treebank paper.
That's probably true.
So it would be interesting to have some combined model.
Yeah, that's true too. Yep. Okay. This talk goes to 1:15.
Yep.
Okay, great.
One
So
would be better, but 1:15 is okay.
wait, one would be better, but
But we can push to that.
okay. In that case, we'll come back to this if there's time, but I want to get to this inference method, so I will skip using topic models to do scientific article recommendation, even though it's really fascinating.
There's a question here.
What's that?
There's a question on
Yeah.
that side.
How does this do for things like Fisher or Bayes, who maybe didn't have much impact following a few years, but obviously pretty important later?
Yeah, so that relates to this question about the envelope of influence. So, we set the envelope of influence to something like 5 years, and something we'd like to do as part of continuing to work on that model is understand how to fit that.
So you're not going to let it be like 200 years to capture Bayes?
No, you would need to actually maybe even estimate a function of some kind of function. So if you want to allow that function to happen, then there's a 200-year mark or whatever. But it might be that we just can't capture that whole thing, which is also an okay outcome. Okay, so in the two methods I talked about and the method I didn't talk about, the process is the same. Positive generative model that captures the kinds of assumptions you want to figure out about in your data, cast whatever it is you're trying to do as a posterior computation in that model, and then approximate the posterior distribution because all the models I've shown you are too complicated to afford exact computation. Again, this picture, I want to now talk about this part of it. How do we infer the posterior once we have data and a set of assumptions that we want to compute about? Okay, as I mentioned before, existing algorithms process document collections in batch, analyze the whole collection, update the model, and repeat. Continue to analyze the whole collection again and update the model. This is inefficient for large collections, and it can't accommodate streaming collections. We need online, or we're now calling this stochastic variational inference, which allows us to analyze millions of documents and lets us develop topic models on streaming collections. And the idea is very simple. Sample a single document, analyze it, update your model, and repeat the process. And again, now I want to explain why. I mean, we could just try this, but why this is an okay thing to do. Okay, so returning to the simple LPA model, for which I'll describe this algorithm, our goal, remember, is to compute the posterior, the conditional distribution of the unshaded nodes given the shaded nodes, which are the words of the documents. And stochastic variational inference builds on variational inference, where we approximate that posterior distribution by positing a parameterized distribution Q over the hidden variables, and then fitting the parameters of Q to be close in KL divergence to the true posterior that we care about. Okay. So in variational inference, that's the basic idea of variational inference. And in mean field variational inference, we assume that each hidden variable is independent and governed by its own distribution. Okay, so I drew that here with these little, whatever they are, these little shaded tiny nodes, where every topic has its own parameter, lambda k. Every word in every document has its own parameter, phi. This corresponds to which topic that word came from. And every document's topic proportions has its own parameter, gamma. All right, so so we've defined a distribution over the k topics and over the d times n topic assignments and over the d topic proportions that contains really millions and millions of parameters for a large data set. And the goal is to tweak all of these knobs so that the corresponding distribution over these variables is close in KL divergence to the real posterior that we can't compute. Okay. How that works in mean field variational inference, the way it usually works is to optimize these parameters with coordinate ascent. We hold everything fixed except for one parameter, and then we optimize that parameter. Hold everything fixed except for another parameter and optimize that parameter and repeat that process. Okay, I'll make this more concrete in a second. So I like to think of these two kinds of variables as local variables and global variables. The local variables are the topic assignments, which topic each word came from, and the topic proportions for each document. These are the variables that are local to each little document in your collection. And in the local step of variational inference, we do coordinate ascent on these two sets of parameters, gamma and phi, where we hold the topics fixed. Okay? So local variational inference takes an article and iterates between figuring out its proportions and the assignments for each word, back and forth, holding the topics fixed. And that's how we get this picture. Okay, that's how we got the picture. That's how we had a bunch of topics, and we took these words, and this is the result of local inference. In the global step, we then aggregate all of the information from these local steps and recompute the topics for the whole collection. This looks a lot like EM with local and global estimation steps. And that's how we got this picture. Okay, we took all of the gammas and phis, just the phis really, from the whole document collection and then updated our idea of the topics. And that's where we get these topics. Okay, so this is the traditional variational inference algorithm for LDA. You initialize the topics randomly in step 1. Then for each document, you do local inference, back and forth between the words and the proportions. And then you update the topics from an aggregate of the information that you got here, and you repeat that process. This is the algorithm that we've been using for many years, and you can see why it's inefficient, because you start out by initializing the topics randomly. So initially, your topics are just total garbage. Then, you spend a long time analyzing your whole collection with garbage topics. You really focus on how well each document in your collection reflects the garbage topics and create parameters for that create parameters for that inference. And of course, those parameters reflect nothing. They just reflect the initial bad topics that you started with. So with millions of documents or with streams of documents, you can't do anything here. You're analyzing the documents with randomly initialized parameters from the get-go. Stochastic variational inference works as follows. Randomly pick a document, perform local variational inference with the current topics, form fake topics, treating the sample documents as though it were the only document you've ever seen in the collection, and then update your topics to be a weighted average of the fake and current topics. Okay, so how does that work operationally? We've got some topics that we've, say, randomly initialized. Choose a document at random and analyze it according to those topics. What does that mean? That means you get distributions of topics for each word, and you get a distribution over distributions of topics for that document. Now you form fake topics from those inferences. What does that mean? That means you pretend that this is the only article you've ever seen, and you create topics based on which topics you thought these words came from. The nuance here is that which topics you think those words came from is based on your topics that you are trying to update, the actual parameters of your variation distribution, but you create these kind of fake topics based only on this document. And then you update the topics to be a weighted average of those fake and current topics. You take those fake topics and you move your current topics a little bit in their direction. Notice, for example, the fake topics are only going to have mass on the words that were actually seen in this document. Okay, so here is again how it works as an algorithm. This is what I just described. And here's why we want to do this. So in the x-axis is the number of documents I've seen at the log scale. So there's 10 times as many documents between here and here as here and here. The y-axis is perplexity. So this is the goodness of fit of some held out set of documents. Our corpus here is 3.3 million articles from Wikipedia, which is a kind of collection that would be really hard to analyze with batch inference. And there are 3 lines on the graph. So here, we took a subset of Wikipedia, 100,000 articles, and we did batch inference. So we started out with garbage topics. We analyzed every article with those topics, and then we plotted the held out perplexity. And notice you have to see 100,000 articles before you can even get the first point on the plot, because you have to analyze every article in the collection before you get a model. Here is then the next iteration of that EM-like algorithm and so on. That's batch inference. And here's online inference. So the blue line is online with the same population of documents, the same 98K, repeatedly sampling documents and updating our idea of the model. And by the time you've seen 100,000 articles, here you've seen basically every article, there's some, we're sampling with replacement, so you're not seeing every article here. We have much better perplexity. And the performance continues. But now, of course, we can look at the whole population of articles, so 3.5 million of them, and that's the green line. And you can see that you get even better perplexity with the green line. By the way, the blue line does better than the red line, even though these are from the same population of documents. And that's not just noise. We saw that over and over again. And it's known in the machine learning world that online inference, stochastic, well, I haven't talked about that yet, but that online inference tends to generalize better than batch inference. Okay, so this plot to me motivates why we would care about this algorithm. Yeah, Jason.
I was thinking there might be another reason for that effect, which is that the batch inference starts with random initialization.
They both
and
do.
so maybe a worse local optimum problem?
That's right. Well, worst local optimum problem is why stochastic methods and online methods tend to generalize better, because you don't commit as much to where you started. There's this randomness.
Well, there's 2 things going on. One is that you're doing it's a stochastic optimization method because you're sampling a new document at every step.
Right.
But the other is that well, I should probably think a little bit more thoroughly about what I want to say. But there's this problem that you might be in completely the wrong part of the space when you're initializing with the batch method.
And you have more of a chance to get out of it with this method. Is that what you mean? I think
what I'm saying is, suppose you initialized using the batch method, and then you continued your optimization
I think you would be stuck.
by doing your stochastic method.
Yeah.
I imagine you might still do worse.
Yes, I think you'd be stuck. Yeah. Yes, I think you're right. Okay, so why does this work? This works because of vanilla stochastic optimization. Okay, we really took the algorithm from 1951 and applied it to variational inference. It's a little more complicated than that, but that's basically what's happening. So I know many of you know about stochastic optimization. For those of you that don't, the basic idea is that when you're optimizing a function, it might be cheaper to compute a noisy estimate of the gradient, an estimate of the gradient whose expectation is the gradient, but has some noise. And you can do that and still get to the optimum of the function by just taking decreasing step sizes in repeated noisy measurements of the gradient. So the example that captures the intuition for me is that if you were here in Baltimore and you were trying to get to San Francisco and everybody's drunk. So what do? You walk outside, see see the first drunk person you can find, and you say, where's San Francisco? And, you know, drunk person just sort of points in some direction. It's almost a random direction, but on average, if you pulled enough drunk people, that direction would be precise. It would be the direction in San Francisco. Again, you've only asked one drunk person. So what do? Well, walk 1,500 miles in that direction. Imagine, you found somebody on the ground, pointed in some direction, walk 1,500 miles in that direction, and everybody is still drunk wherever you ended up, and ask another drunk person where to go. Again, points in some random direction, walk 750 miles in that direction. Keep on repeating this process, and you'll eventually get to San Francisco. That's what Robinson and Monroe proved in 1951, and that's the same idea here. The way, the objective function, the KL divergence between the variational distribution and the true posterior is a sum of terms, one for each document. And so we get our drunken corpus by just asking for one document at a time, a random document, computing the gradient with respect to that random document, and moving 1,500 miles in that gradient, then asking for another random document and repeating that process. So we wrote about it in this paper, Hoffman et al. 2010. That process leads to that algorithm that I just described for you. With these, the step size is the weighted average of the fake topics and the real topics. Okay, so stochastic variational methods are a general way to approximate posteriors in massive data sets. There's no need to process the whole data set in advance. It easily links to things like web APIs and other data sources. It's also easy to adapt this to other kinds of models. So we've now worked on this in a community detection model of social networks and in Bayesian non-parametric models. So you can fit a hierarchical Dirichlet process to millions and millions of data points with this algorithm. And there's software available online that implements it, and you can read about the papers here. Yeah, there was a question.
What happens if you make gradient using aseptic documents instead of mini batches?
Yeah, that's right. That is what we're doing. So there are mini batches, and you can control how much noise there is through these mini batches. That's right. Look at this paper for the details about this algorithm. Okay. So to summarize, hierarchical Bayesian models are a powerful way to explore, summarize, and search large archives of documents. In general, probability models provide an intuitive language for expressing assumptions about observed and hidden variables. You know, I showed you LDA and a few variants of LDA, but really what we're doing is articulating assumptions through graphical models. And algorithmic advances in approximate posterior inference, I have the details about how this stochastic variational inference algorithm generalizes at the end of this slide, if you're interested. They let us apply complex models to very large real-world data sets. Some open research directions are here, but it's 1 o'clock, so I'll just stop and ask some questions. Thanks.
So what is the effect of distributing like this stochastic gradient of algorithm variational inference over like many machines and CPUs?
Okay, so that relates to the other question. The batch variational inference is parallelizable in a trivial way, right? Because you could just take your current setting of the global parameters and farm your data out to a bunch of machines. Each one does a little local variational inference and then aggregates it back. It's like the MapReduce setup. Here you can employ that with mini batches. If you had a mini batch of 100, you could use 100 machines. Each one analyzes a single randomly sampled document and then throws back the local parameters to be aggregated to get you the next global parameter for the next mini batch. Yeah.
Is resampling important?
What do you mean?
Like you're only allowed to use something once, like the edge is wrong, and there's still a lot of
So, in the theory around this algorithm, the expectation of the noisy gradient has to equal the real gradient. And that leads to sampling with replacement, or resampling. But if you have but nothing stops us from running this algorithm with a stream of documents where we know we're never going to see the same document again. It seems to work. It seems to fit a model that gets better and better. But we haven't I don't know. It's on
You
here.
might see the same document again because somebody can write it again.
What's that?
You might see the same document again because somebody.
Yeah, that's right.
can
Someone
write it
could
again.
write it again. Right.
I mean, I think the theory is okay, actually. You take a stream of documents, and that's each one is being generated from the generative process over documents.
That's true of people writing documents. Yeah,
Yeah.
that's right.
That's assuming you're going to run process checks that you're working with dynamic case for topic.
Yeah, so that's the difference. So if the underlying data generated distribution changes, yeah, you're right, Jason. The theory is okay in that case, as long as you assume the documents are going through the same process throughout history. If the data generating distribution changes, then it's trickier. There are ways of doing stochastic optimization in the face of that. We haven't explored those yet.
In fact, I was going to ask you, the dynamic topic model that you mentioned where the beta Ks were
Yeah.
temporally dependent, how would you do the online version of that?
Well, it's tough. So the generic model that we derived online inference for is one where every pair of nodes is conditionally conjugate.
Okay.
So I can write down in closed form the conditional distribution of each hidden variable given its Markov blanket, given the nodes around it. And in the dynamic topic model, that's not the case. So the variational inference algorithm there is more complicated. So what we're working on now are more black box-like methods of handling non-conjugacy, which will then let us fit things like dynamic topic models with this online method. You can think of it in two ways. One way is if you had a changing data generating distribution, that history is progressing, and I want to basically adapt my model to how the topics have changed. There I would probably look at the stochastic optimization literature to see how they handle that kind of situation, where the model is changing underneath your feet. But the model I showed is one where you're actually interested in retrospective estimates of posterior expectations. And in that setting, I think the way to do it is to say, okay, look, I've got this corpus, like JSTOR. JSTOR has a corpus of millions and millions of articles, spans 500 years, but they're interested in what you think of the article in 1669. So you can perhaps fit a more ambitious model by subsampling across time repeated documents and then updating that whole sequential model. Those are two separate ways of dealing with time series.
What I thought perhaps you might say is that you could organize your corpus in time, even when you're doing the online version, and a steady, large gradient could be an indication of an underlying topic shift. In other words, normally you expect small updates to your model, but if you see a long run of large updates, that's sort of a signal that, I don't know, it could be either one. It could just be a standard model update happening, you're sort of escaping from a basin or something, or it could be that there's a topic shift going on.
It's tricky though, because when you get to Sausalito and you ask drunk people how to get to San Francisco, you can only go a small amount of distance, so that you're already going to see small changes. But it's true. Maybe if you could estimate the real gradient and look at that would be perhaps a way of incorporating time series. It's an interesting problem in a way. I think that's something we haven't solved at all. Yeah.
So one thing I was hoping you'd get to in explaining more in your method, but in stochastic variational inference, you said that you do the average between the model parameters and the model on your fake topics.
Yeah.
And how do you know which fake topics should line up with which real topics?
So
that averaging.
I'll explain it more clearly. So, okay. Here are your topics. These are the topics, your current estimate of the topics. That's your model. Grab a document, estimate the topic proportions and the topic assignments of each word in that document using these topics.
Okay.
Okay, so now you've done that. Let's say your document contains 5 words. The cat ate the fish. Okay? Now, by fake topics, so now you have for each of those 5 words an estimate of which topic they came from among this set of fake topics, of this set of real topics. Now, compute by fake topics. What I mean is, take your estimates from the cat ate the fish and compute topics from them. So now you get a set of fake topics here. They line up because you've estimated which topics each word came from these real topics. But now these topics here, the fake topics, they only have probability mass on cat, ate, and fish. Okay? So for all your 100 topics, you have different probabilities of cat, ate, fish. These are weird-looking topics, right? So now, here are my real and fake topics, compute a weighted average of the two. So you're going to just move your real topics in some way towards cat, 8, and fish in different ones, and then you repeat the process. So that's why they line up. Does that make sense? Yeah.
So am I guessing right that this interpolation procedure happens to be the procedure for following the stochastic gradient?
Yeah, okay.
For this variational method. So you're not motivating it by solving for this one document and then interpolating.
No, that's right. So the method is so simple that I like to present it first. But right, here's how it works. This is batch variational inference in general. Compute local variational parameters for each data point, then compute global variational parameters. The key idea that I haven't yet mentioned is the natural gradient. In the variational objective function, the natural gradient with respect to the variational parameters leads to the following fact. If you take all of your variational parameters, and instead of doing coordinate ascent inference, optimizing each one holding the others fixed, you computed those coordinates en masse. You computed those coordinates all at once, and then you subtract these two vectors. That gives you the natural gradient of the variational objective function. So what that means is that, right, so that fact plus the usual stochastic variational inference update, which is here, where you take your old parameters and take the gradient, the noisy estimate of the gradient, and multiply by a step size. Those two things together lead to that fake topic, real topic story. And this epsilon t, the step size in the stochastic optimization algorithm, that's how you weight those averages. That's how you weight the two. I can point you to this paper we're writing about this that has this kind of general story. That's right. Yeah.
So how does this work for not getting stuck in like a local optima that are like erroneous? Like your drone person analogy, what if you asked a bunch of drone people that thought San Francisco was actually Chicago or something, and always would point in that direction?
Right. So the way it works is that, first of all, in the drunk San Francisco story, I assume that the United States is convex. Okay? It's convex. Right? There's only one way to get to San Francisco. It's the top. And that, again, the expectation is that the right gradient comes out. That if you poll these drunk people 200 million times and average the direction they point in, they're going to point in precisely the right direction to San Francisco. Here we're not so lucky because this objective function is not convex. It's got lots of local optima. And so you do what we've always done, which is either run it several times and hope, or just run to a local optimum and then check that local optimum in ways that don't depend on getting to the right local optimum. In other words, evaluate the predicted performance of your model plus variational inference, which I think is the right way to think about these things anyway. Because we actually don't even care about the real posterior. Even if we got the real posterior, it might not be good at either. What we care about is that the modeling assumptions plus the technique we have to use because we can't compute the thing we want to compute about those modeling assumptions, that leads to good performance on some tasks or good exploratory properties. But yeah, so local, and now as to why we get to better local optima, I mean, that's something we're speculating about. In machine learning, they've seen that in a lot of different settings where you get better generalization performance when you use stochastic gradient. And it seems like this is another case of that, but there might be other reasons.
No other questions? Let's thank David once again.